So continuing with our quantum mechanics, we're now going to look at the Sx, which was our right-lefts, and Sy, which was our in-outs, in a little bit more detail. Okay, just to remind you, we've had two quantum rules so far. One is the states of a system are all of the normalized complex vectors in a complex vector space, which we call the Hilbert space. Those are all the states. Remember, that's everything you can measure about that system. And then we also had, remember, this dot product between A and B is the probability amplitude of measuring state A if you're already in state B. And when you multiply it by its complex conjugate, which is the magnitude squared, is the probability of measuring state A if in state B. Okay. Now, last time we looked at just the Z when we had our sensor straight up and down, which was our sensor, and we called, when we got a +1 here, we called it an up, and we said, we defined it this way, 1, 0, and down, 0, 1. And when you dot these two, you get these things were orthonormal basis vectors for the Z direction. Anytime these two are the same, you're always going to get 1. But these form an orthonormal basis vector. So when you dot them with themselves, you get 1, down, down. But when you dot it with the other one, you always get 0. Okay, so this was just for the Z basis. Now I want to look at the X basis when we turned it sideways. Remember, when we turned it sideways like this, we had it like that. Remember, we said if we get a +1, we called it the right state, right here. And when we got a -1, we called it the left state. Now, we want to know is what are the column elements for the right and the left? They can't be these right here because these two can't be the same right here because remember what we said before was we said if we were in the up state and we measured right, and we already said that probability was 50% or 1/2. So if they were the same, you just get 1. So right and up cannot be the same. Also, if we were in up and we measured left, remember we said we got 50%. Oops, these are squareds. You got 1/2. Or if we were in the down and we measured right, that was also 50%. Or we said if we were in the down and we measured left, that was also 50%. So this has got to be true. Not only that, this has to be the orthonormal basis vector for the X direction. So this is the X direction. So we know since they're orthonormal, we know that right has to equal 1, and when you dot it with the other one, right-left, that has to be 0. Same with left-left, has to be 1, and left-right also is 0. They form an orthonormal basis vectors right here. Okay, so how do we get our states for right and left, the column? Let's look at right first. So if we look at right, I don't know what it is. I do know it's 2 elements, just 2 elements. So why don't we just say it's A and B, and we'll try to figure out from these rules what A and what B are. Well, if we look at this right here, first of all, what is right-left? Sorry, right-up. Right-up without the magnitude squared. Remember, to turn the ket into a bra, you turn it into a row, and you do the complex conjugate. So it's A star, B star, times our up, remember, which was 1, 0. Okay, and so this just gives me a star plus 0, a star. Okay, but we want to take the magnitude of it, so that would be the magnitude of this, which is a star times a, which is a squared, and that equals 1/2. Okay, so what is a right there? Well, one solution is 1 over the square root of 2. A equals 1 over the square root of 2. There are other solutions to this too. Minus 1 over the square root of 2 would work right there. I times the 1 over the square root of 2 would work. Minus I times 1 over the square root of 2 would work too. But we are going to define it this way. This is the way it's defined. So A is 1 over the square root of 2. Okay, now we need to find out what B is right here. Well, why don't we do the right and the down? This one right here. Right and the down would just replace that with 0, 1 right there. So we'd have A star, B star, and then you'd have 0, 1 instead, because we're doing it with down. And that would just give me B star. Okay, for the same reason, this times its complex conjugate, it would have to be 1/2. So again, there were a lot of solutions, but we'll use the 1 over the square root of 2 also. So we'll use the B, just define it that way. We could have defined it differently, 1 over the square root of 2. So there is my right vector. So my right vector will be 1 over the square root of 2, 1 over the square root of 2. Now I could have brought out the 1 over square root of 2 and just said 1, 1, but anytime you have two vectors and they have equal magnitudes, it's going to have to be 1 over the square root of 2 and 1 over the square root of 2. Why? Because remember, this squared plus this squared always has to equal 1. So 1/2 plus 1/2 equals 1. Now, if we do it for the left, the same thing for the left. Left up should equal 1/2. Well, what do we want to call left? How about if we just let left equal AB? AB. Okay, and find A and B. Well, if we just come along and use this, we're going to do left up, which is exactly like this one, right up, which is going to look exactly like A star, which means A is going to be 1 over the square root of 2. We have other solutions here, but we're going to pick the A equals 1 over the square root of 2. So A equals 1 over the square root of 2. And then when we put in the down, it's going to look exactly like this right here. And we're going to end up with B squared equals 1/2. But we can't pick 1 over the square root of 2 because that's what we picked for the right. But we can pick the minus 1 over the square root of 2. So we'll let B equals minus 1 over the square root of 2. So that way the left equals 1 over the square root of 2 minus 1 over the square root of 2. Now just to make sure that they are, all these should work out right here. That is, if we dot right with right, we should get 1. Well, let's see. If we dot right with right, remember, the bra of right, you just flip it and take the complex conjugate, but that's real, so you don't have to do anything except just flip it. 1 over the square root of 2, 1 over the square root of 2, and then times our ket of right, which is 1 over the square root of 2, 1 over the square root of 2. We get 1/2 plus 1/2, 1. Okay, which is what and then if we do right with left, we get 1 over the square root of 2, 1 over the square root of 2, left, which is 1 over the square root of 2, minus, because we said the second one was minus 1 over the square root of 2, which is a half, minus a half, which is 0. Okay, so this right and this left form our orthonormal basis vectors for the x direction. Now I could have written right and left in terms of ups and downs, because I could write this as 1 over the square root of 2, 1, 0, plus 1 over the square root of 2, 0, 1. You noticed if I put this together, it'd be 1 over the square root of 2, 0, plus 0, 1 over the square root of 2, combine them together, I would get that. And you remember, this is up, that's down, so this is 1 over the square root of 2 up, plus 1 over the square root of 2 down. So I could have written right as that. Just like I could have written left, we could have written left as 1 over the square root of 2 up, minus 1 over the square root of 2 down. Down right there. So this was my right, this was my left. You noticed if I just added those two together, right plus left, right plus left. Well, then I'm just adding this plus this. The downs drop out, and it's just 2 of these. 2, and that's just 2 over the square root of 2 up. Or, if I multiply everything by the square root of 2 over 2, then I got up equals. The square root of 2 over 2 is really just 1 over the square root of 2. So this is just 1 over the square root of 2 right plus 1 over the square root of 2 left. So I can write ups in terms of rights and lefts, or I can write rights in terms of ups and downs. Or if I subtracted these two, right minus left, well, if I subtract them, the ups drop out, and that gives me 2 of these. So I get 2 all over the square root of 2 down, or I can solve for the down. Bring this over, it's square root of 2 over 2, which is 1 over the square root of 2. 1 over the square root of 2 right, minus 1 over the square root of 2 left. So I got ways of going from left and rights to ups and downs, or I can go up and down to rights and lefts. We can go back and forth right here. Okay. Well, let's say now that we have this, let's do an example right here. Let's say we have, say, psi, some state. It's in terms of rights and lefts. So I'll just make it I over 5 right plus the square root of 24 over 5 left. Okay, now, is this normalized? This times its complex conjugate plus this times its complex conjugate has to equal 1. Well, this times its complex conjugate is 1/25. This times its complex conjugate is 24/25. 1/25 plus 24/25 is 1. So this is normalized. Remember, all of our vectors always have to be normalized. Okay, so what do we want to find? Let's say we want to find what is the probability of measuring right. Probability, right there, we're in the state psi, and we want to measure right. So psi and right, that's what we want to put. So we want to be right here, and we want to put psi there. And we want to square it. Okay, so we'll just plug this right into here. And so that's equal to right. And then we have psi, which is all of that. I over the square root of 5 right plus the square root of 24 over 5 left squared. Okay. Now I can break this right up into right and right left. So we still got the square here, but right is 1. So this first term is just I over the square root of 5. And then right left is 0 because they're perpendicular. So that's it. And then we find the magnitude squared. This times its complex conjugate is just 1/25. 1/25. So the probability, let's just write it like this, the probability of measuring right is 1/25. Matter of fact, anytime you're in a state like this, the probability of measuring this is just going to be this times its complex conjugate. The probability of measuring the left will be just this times its complex conjugate. If I asked what is the probability of measuring left, you already know what it is, because it's got to be the rest of the probability, which is just 24/25. So the probability of measuring left is 24/25. You know, they have to add up to 1 also. Well, what's the probability of measuring up? Probability of measuring up, though. Well, what does that mean? It means we have to do up with our psi. Square it. So that's what we have to do. Well, you know, if I plug in my psi, we're going to have just like this, except there's going to be an up here. So we got an up, and then we've got I over the square root of 5 right plus the square root of 24 over 5 left. Okay, but I don't know what upright is right here. But what I can do is I can turn my rights into ups and downs, and I can turn my lefts into ups and downs. So this would become up, and then right here we get I over the square root of 5, except in place of right, I'm going to put my right was this. Remember, that was my right. So I'm going to put that in place of it. So that's 1 over the square root of 2 up plus 1 over the square root of 2 down. Okay, so there's my plus the square root of 24/5 in place of my left. Again, I want to change the bases because I know what all the ups and the up downs are. And then we have left, which is right here, 1 over the square root of 2 up minus 1 over the square root of 2 down. Down. Okay. So now I can start doing the dot products. Remember, all the dot products are going to be 1 or 0 now. So we've got, first of all, this dotted with that. That's 1. So all I have is I over the square root of 10. That gives me 0. That gives me just 1, but I have a square root of 24 over 5 square root of 2. So you got plus the square root of 24 all over 5 square root of 2. And then the last one, which is 0. Okay, that's squared. Okay, I should probably get a common denominator before I try to square this out right here. So if I get a common denominator here, it looks like I need a 5 here. Let's see, I need a 5 here and a 5 there. And then I need over here a, what do I need? I need a square root of 5. Square root of 5 and a square root of 5. Okay, so that gives me 5i plus the square root of 24 times 5 is 120. Square root of 120 plus the square root of 120 all over 5 square root of 10. 5 square root of 10. Squared. Okay, so now I'll multiply it by its complex conjugate. So if we multiply it through, so now we have 5i plus the square root of 120 all over 5 square root of 10 times the complex conjugate minus 5i plus the square root of 120 all over 5 square root of 10. Okay, and now when we square out the numerator, the cross terms always drop out, and it's always the first squared plus the second squared. The first squared is 25. The second squared is 120 all over the bottom squared. Well, that would be 25 times 10, which is 250. So this would be 145 over 250. 145 over 250. And I guess I could put 5 goes into both of these two. 5 goes into this 50 times. 5 goes into that 29 times. So that right there, it's a little over 50% right there, but that would be the probability of measuring, what do we say? The probability of measuring up right here. Now, if I ask what is the probability of measuring down, I don't have to redo all this because it's just the probability of measuring up plus the probability of measuring down better be 1, so it better be the rest of it. So the probability of measuring down should be the rest, 1 minus that, which is 21/50ths. 21/50ths. So there's the probability of measuring down right there. Okay, so there is right and left, and here we can move it to ups and downs if we wanted to. If I wanted to do this instead right here, I could have turned my ups into rights and lefts, and I would have come out with the same answer. So I could have taken my up, which was 1, 0, and turned it into rights and lefts. Actually, I could have done it right here. Remember, if I turn this into a bra, I take the complex conjugate, well, that didn't do anything, and just turn these two into bras. And then multiply them out. I could have done it that way too. Okay, so there is x, but now let's look at the y. That's the in and out. So if we kind of, it's kind of hard to draw it here, but now we're kind of going into the board, and here's our sensor right there. Okay, and so we said if we get a +1, we called it the in state. And if we get a -1, we called it the out state. So those were our two states. Again, they should form an orthonormal basis for the y direction. So this is the y direction. And so what does that mean? That means I equals 1, and IO equals 0, and OO equals 1 and OI equals 0. So we do know that. We also know that if we were in the upstate and we measured this, there was 50% in and 50% out. So we did know that if we were in the upstate and we wanted to measure out, or in, it doesn't matter, this gave us 50%, 1/2. Same with all the rest of them. Up without, down within, down without. Same with right within, right without. You know, they're all over 50%. So I don't know if I need to go through all this again, because what are we going to do? We're going to assume in is AB, just like we did before. We want to find the column for, we'll just call it AB. Okay. We'll work it out. It'll look exactly the same. We don't have to do this again. What did we get here? We got A to be 1 over the square root of 2. It will still be, we'll define it as 1 over the square root of 2. Now, when we want to get B, again, we're going to come down to where B squared is equal to 1/2, just like we had before. A squared, we had B squared equals, that's how we got B equals this. But we can't pick 1 over the square root of 2, because then it would look just like the right. And we can't pick minus 1 over the square root of 2, because then it would look just like the left. But we can pick I times 1 over the square root of 2, because I times 1 over the square root of 2 would make this equation correct too. So my B will be I all over the square root of 2. So that means my N will be 1 over the square root of 2, I over the square root of 2. Now, when we do the out, again, we're going to get the same thing, except the only way what I can do is back to here, when we get the A will be the same, but B, there's one more solution that'll work here, and that's minus I over the square root of 2. Remember, there were 4 solutions for this right here, so we'll use the minus I over the square root of 2, so that means my out will be 1 over the square root of 2 minus I over the square root of 2. Now, just to see if these guys work right here, let's go ahead and pick like I. Well, what do? For I, we flip it, and then we take the complex conjugate. So that's going to have to go to minus. So it becomes 1 over the square root of 2 minus I over the square root of 2. Don't forget, when you flip it, you got to take the complex conjugate. And then our regular I, which is this, times 1 over the square root of 2, I over the square root of 2. Okay, so what does this give me? This gives me 1/2. And then this right here. Remember, minus I times I is a plus 1. So it's plus 1 over 1/2. So it's 1. Just like we said, I is 1. If we were to take the I and then the out, then this would have been just a minus right here. And minus I times minus I is minus 1/2, right? That would have been a minus, and you would have gotten 0. So then it seems to follow this. These are my orthonormal basis vectors. This one right here, and this one up here for the y direction. And again, I could write these things in terms of ups and downs. N is 1 over the square root of 2 up plus I over the square root of 2 down. Okay, and then I could have done out 2. Out would have been 1 over the square root of 2 up minus I over the square root of 2 down. And I could have written in and outs in terms of rights and lefts, and you could have done it for all possible combinations right there. So that handles all the possible combinations for that. Okay. Well, what happens if you're in some other direction right here? Not in the x, the y, or the z. Well, they have something called a bloch sphere. Bloch sphere is sounds like an oxymoron, bloch sphere. But when I say block, I don't mean B-L-O-C-K, I actually mean B-L-O-C-H. That's what I mean by bloch sphere. So if we have let me put in an axis right here. I'm going to call this the z, or the up. Remember, this was our up direction right here. This right over here is the y, which is the in direction. This is the x, which is the right direction. And then, if I can follow this straight down, this is the down direction. And if I followed this one over here, this would be the out direction. And if I followed, remember, x is really coming out like this, but I can't draw it that way. And if I follow it back, that would have been the left. Okay, so now, suppose you put a big sphere on, a unit sphere. A unit sphere. So this is some sort of a unit sphere. And so this vector, any vector along this unit sphere is one of these ones in our two-dimensional space. And let me just pick it to a specific value. I'll just say it's coming out to here. So I'm going to call this angle right here theta. And then if you bring this vector down to the xy plane, it kind of swings across this way, some angle phi. It's almost just spherical coordinates right here. Well, if this is your psi right there, and you want to write it in terms of ups and downs, well, then the equation is, it's equal to psi is equal to the cosine theta over 2 in the up plus e to the I phi times the sine of theta over 2 in the down, where theta and phi are given by this right here. This will give it, so if I set up my sensor and I put it right here, so my arrow was pointing, so I put this sensor so it was pointing right out like that, and I got a 1, this is what the state would be in. Just to check it, let's just pick one going straight up. So if you're going straight up, that means theta equals 0. And it doesn't matter what phi is because there's no phi if you're just sitting there going like that, so it doesn't matter on phi. So what is psi? Psi is equal to the cosine of 0 over 2, which is just cosine of 0, which is just 1, so that's just up. And then you plug in 0 over here, that's just 0. Okay, so, which means you're just up. That's what we said we were. We were just up. Suppose theta is 90 degrees, pi over 2, and phi is 0. So now we're right along the x direction. So phi is equal to 0. This better give me the right. Let's just see if this gives me the right up here. Well, what do we get? We get psi is equal to, we get the cosine of this over 2. That's cosine of pi over 4. Cosine of pi over 4 is 1 over the square root of 2. Up. And then if you plug in 0 there, that's just 1. And then you just get sine of pi over 4, which is 1 over the square root of 2. 1 over the square root of 2 down. And that was my right. Remember, that was my right there. There was my right. Okay, well, how about if we wanted to get the in direction right there? The in, that's when theta is 90 and phi is 90. Theta equals pi over 2, and phi equals pi over 2. Well, let me just see. If we plug in theta equals pi over 2, we get psi. You get cosine pi over 4, which is 1 over the square root of 2, up. And then we get e to the I pi over 2. E to the I pi over 2, we said was I. Remember, we said e to the I pi over 2 was cosine pi over 2 plus I sine pi over 2. Well, that's 0 and that's 1, so it's just I. So it's just plus I times the sine of pi over 4, which is 1 over the square root of 2 down. Which is exactly what I had for my in, which was right here. Here's my in. So if I wanted to get down, whatever I wanted. So I could make, by taking my sensor over here and putting it at some strange angle, I could prepare any state I wanted. Suppose we came along here and we just said, well, let's let theta be, let's say pi thirds, pi over 3. Let's let theta equals pi over 3, and let's let phi equal pi over 3. Okay, just try to make easier ones right here. That would mean that I'm coming down pi over 3, which is 60 degrees, and then I'm going over 60 degrees, so it's coming out here someplace. So what do I get? I get cosine, so we get psi is the cosine of pi 6. Cosine of pi 6, I think, is the square root of 3 over 2 up plus e to the I pi over 3, e to the I pi over 3 sine pi 6. That's 1/2. 1/2 down. Or if I wanted to write, if I didn't want to leave it as e to the I pi over 3, I could have done what we did up here. E to the I pi over 3 is equal to the cosine of pi thirds. Cosine of pi thirds is 1/2 plus I sine of pi thirds, which is the square root of 3 over 2. Okay, so I could have put that into here. So that means psi is equal to the square root of 3 over 2 up plus 1/2 plus I. Let me pull the 2 and the 2 out, so I got a 4. 1 plus I square root of 3. 1 plus I square root of 3 in the down. So if I wanted to make that state, I could just put my sensor there and then put my electron there, and if I get a +1, that's what I want. If I got the -1, it would have been pointing in the other direction. But I'll just pick the one that had a +1 on it. Okay, so now that we have that, what can we do? Well, let's just say we want to measure something. What do we want to measure? We want to measure the probability of being in the up state. What is the probability of being in the up state? Right there. Well, it's just this squared right there, which is just 3/4. What's the probability of being in the down state? It would be this times its complex conjugate, but I don't even have to do it because I know it better be 1/4. Because I know this probability plus that has got to be 1. So the probability of being in the down state would be 1/4. Well, what if I wanted to measure the probability of, say, being in the right state? Probability of being in the right state. Well, what I do is I just turn my ups and downs into rights and lefts. So that would be the square root of 3/2. And I turn my up into rights and lefts, my ups into rights and lefts, which is right there. 1 over the square root of 2 right plus 1 over the square root of 2 left. Plus 1 over the square root of 2 left. Okay, that takes care of this, plus 1/4. 1 plus I square root of 3. Down. I got to turn my downs into rights and lefts. Down is right here. It's 1 over the square root of 2 right minus 1 over the square root of 2 left. Minus 1 over the square root of 2 left. Okay, now I guess I'll just combine my rights together and my lefts together. So I shouldn't say this isn't the probability yet. This is still my psi. I shouldn't write it as the probability. What I want to get is the probability to right, but this is still my psi, but I've written it out in terms of rights and lefts. Okay, so now we have, if we pull out all the rights first, we got, let me factor it out, the right. And we got square root of 3 over 2 square root of 2 over 2 square roots of 2. That takes care of this term, plus I've got all of this, plus 1/4 1 over the square root of 2, 1 plus I square root of 3. Okay, that's how much right I have, and then I'm going to have so much on the left, plus the left times some stuff. I don't really need to know what that stuff is, because once I got the probability of the first one, I know what the probability is of the second one. So really all I have to do is just take this and multiply it by its complex conjugate. That would be the probability of measuring right. Let's do that right there. Let me just get a common denominator. Let me put a 2 and a 2 there. So I'm just going to look at this right there, because and so all I have is 4 square root of 2. And in the numerator, I have 2 square root of 3 plus 1 plus I square root of 3. Let me kind of put the parentheses like that. Okay, and all I have to do is find the magnitude of it. So multiply it by its complex conjugate. If I multiply this by its complex conjugate, it's this term squared, 2 square root of 3 plus 1 squared, plus the last term squared, plus 3, all over this squared, which is 2 times 16, 32, 32. Okay, I guess I can, it's not going to come out nice, but at least let's square that out right there. The first term squared is 4 times 3, which is 12. Then you get the cross term, which is 2 times the first times the second, which is 4 square root of 3 plus 4 square root of 3, plus the last term squared, plus 1, and then we still have the plus 3 all over 32. And then 12, 13, 16, plus 4 square root of 3 all over 32. Looks like there's a 4 that goes into each one of those. 4 goes into that 4, plus the square root of 3 all over 4 goes into that 8 times, which is, what is that? It's a little bit, it's more than, well, this is 1.7, so this is 5.7 all over 8, which looks like, I don't know, if I had to guess, somewhere around 60%. It'd be somewhere around 60%, which means that the probability of getting left would be the other 40%. Okay, so there is how we can find the state. This is very important for, remember, everything we're doing, these states are qubits. They're just 2-bit systems. We call them quantum bits, and so we can use them for quantum computers, and this is how we can initialize a bit if we wanted to, by putting it in some direction relative to our coordinate system and putting our sensor there. We could initialize bits this way, qubits if we wanted to. But I wanted to actually show an actual experiment now. I have right here some polarizers, just like Polaroid sunglasses right here. Polaroid sunglasses have an axis to them. Now these work with photons. We're not talking about electrons now. All this works with photons too. And usually when you went through this in optics, they said, well, if the electric field was like this, it went through. If the electric field was like this, it didn't get through right here. But remember, photons, light is a particle too. And so we're throwing one particle through. And so we can say that it's really a two-state system. Either the photon gets through or the photon doesn't get through. Now we could call, if it gets through, that would mean it's in the horizontal, because I've got these lines horizontal. So there's a horizontal state and there's a vertical state right here. If the photon is polarized vertically, it wouldn't get through here. If it was polarized horizontally, it would get through there. So these would be like my basis vectors. That is, HH, it'd be my orthonormal basis vectors would be 1, HV would be 0, and same with VV would be 1, and VH would be 0. So let's just say we have some unpolarized light that's over here. If it's unpolarized, it's got both of these in them. So it's in some sign. If it's completely unpolarized, it has just as much horizontally polarized light as vertically. Remember, when they're the same, it's 1 over the square root of 2. So this is just 1 over the square root of 2 horizontal plus 1 over the square root of 2 vertical. So that's what the state would be before it ran through here. Now, the only light that's going to get through here is the horizontal one. The vertical one won't get through, so when any light that gets through here is just H. So I can say, what is the probability, given this, that you'll get H right there? Well, we do the same thing. We just put in our H, and then we put in our psi, and we square it. Okay, so if we do that right there, now we'll do it right here. And then we'll switch over. So here I got H. And then we've got all of this. That's my psi. 1 over the square root of 2 h plus 1 over the square root of 2 v. And then we want to square it. Okay, we already know hv is 0. hh is 1. So everything in here is just 1 over the square root of 2. When you square it, you get 1/2. So if the intensity here is I naught, the intensity here is 1/2 I naught. So it cut the intensity down by a factor of 2, and that's why it looks tinted right here. That's why you can use it. Cuts down on the amount of light right there. Okay, so now let's come over to here, because I want to have more than one of these right here. So we already have, just do it right here, we have a horizontally polarized one here, and we had our psi out here, which was half, it was completely unpolarized. It was 1 over the square root of 2 h plus 1 over the square root of 2 v. Okay. And then when it got through here, it was all in the horizontally. The vertical didn't make it through, so it's all that state. And we said if this was I naught, then this was 1/2. The probability of getting through was 1/2, so you only get half the photon, so it's 1/2 the intensity. Well, so now this is what the state is. Now let's say I have another polarizer out here. But this one is vertically polarized. Right here. Now we know what our state is now. It's psi, it's h right here. And I know when it comes out of here, it's got to be a v if it's going to come out, because the h's won't make it out. So if I just ask, what is the probability that this gets through that one? I have to say we're in the state h. What is the probability of measuring v? So we're in the state h, and we want to measure v. Well, we already said that these two were perpendicular to each other, so this is just 0. And so if you look, here I have two polarized lenses perpendicular to each other. Let me just hit the lights. And turn on the screen. And you can see with just, there's one of them and then the other one, and there they put it together. You notice if I rotate it, if I rotate them so they're parallel, it's still only half. You don't lose it going to the second one. But if I rotate it, keep rotating it so that they're perpendicular, and you notice no light gets through. Okay, so now, let's put a third polarizer in here that's in the middle, that's rotated up 45 degrees. So this one is, these were horizontal, this was vertical, and this one is rotated up by 45 degrees. Okay, so now when we run it through here, that's like our sensor being rotated. So we have a different basis vectors for this. Our basis vectors here won't be horizontal and vertical. I guess they'll be, I don't know what I should call that, diagonal right and diagonal left, maybe. That's what I'll call it. So this one is, the two basis vectors are diagonal right, maybe I'll write it like that, and diagonal left. These guys right here should be orthonormal basis vectors. That is, if I dot this with this, I should get 0. When I dot this with itself, I should get 1. And when I dot this with itself, I get 1. Okay, so now I want to know what's the intensity just getting through this one right here. I was in H. I know when I get over here, I'm going to be in diagonal right, because this is the way I have it tilted. I know it's over here, it's diagonal right. So what do I have to do? I have to change the bases. I have to write H in terms of these two vectors right here. Well, since I noticed I tilted it up 45 degrees, there's just as much diagonal right as there is diagonal left because I'm at 45 degrees. So I can write H as 1 over the square root of 2 diagonal right plus 1 over the square root of 2 diagonal left. There's just as much since I'm at 45. If I was at a different angle, it would be different right here. Okay, so that's what my H is. And so now what I want to do is I want to say what do we want to calculate? To see how much goes in there, we want to say if we were in state H, what's the odds of getting diagonal right? Diagonal right. Right there. That would be the probability. Okay, well, if I just plug this right into here, what are we going to get? We're going to get this dotted with that gives me 0. This dotted with this just gives me 1 over the square root of 2. And then we square it. So this is just going to give me a half. Well, since my intensity was already 1/2 I naught, and if it cuts it by another half going through that, it's going to be 1/4 I naught. So the I right here, I would be 1/4 I naught. Okay, and now we're in the state diagonal right. Okay, now I need to know how much I was going to get through this one right here. Well, I could write diagonal right in terms of H and V. It looks like a diagonal right is half, since it's 45 degrees, I could write diagonal right as 1 over the square root of 2 V plus 1 over the square root of 2 H. Since it's rough at 45, it's equal amounts. So now, what do I want to calculate? I want to get what is the probability of measuring V if you're in diagonal right. So you would use the probability of measuring V if you're in diagonal right. Well, if you put this thing over to here, the V with the H will be 0. The V with the V will give me 1. This will give me 1 over the square root of 2. When I square it, it'll give me a half. So there's another factor of a half dropped. And so it looks like the intensity would be 1/8 I naught. 1/8. This is the intensity here, 1/8 I naught. So it looks like I knocked out half, half, and half. So by putting this in, now I get at least 1/8 of my intensity out. When I take this out, I don't get any light through because these two were perpendicular to each other. So let's just make sure we get that with the third one in. So there's my 2. And now I'm just going to stick this one in between it at an angle right here. You notice right here, oops, it won't stay on there, but oops, I'll put that one back on there. And if I squeeze this in, oops, there's 2 of them, and then I squeeze the third one in right there. See how that third one right there allowed light to get through. So we can even do all this with polarizers. Okay, so any two-state system, we can look at this right here. It doesn't just have to be electron spins. But remember, so I could make a quantum computer with polarizers, or I could make maybe a quantum computer with electrons right here. Okay.